Hello, this is Venkat again. I'm a battery scientist at Berkeley Lab. Last week we posted a video where we asked you to send us all your questions about batteries. We got quite a few. Thank you so much. Today I'll answer a few of them. We had quite a few questions on the energy storage hub that was announced 2 weeks ago, where Berkeley Lab is partnering with Argonne National Lab. Bruce asked, what do you mean when you say you're going to make a battery that's 5 times energy density at 1/5 the cost? Let me answer that in this way. Today we have electric cars like the Nissan Leaf that can go 70 miles in one charge. We really want to go as much as a gasoline car, which would be 350 miles. So that would be a battery that has 5 times the energy density. So that's what we're shooting for. When you ask the Department of Energy what the cost of the battery ought to be to make everybody drive an electric car, it turns out the batteries have to be somewhere in the range of $125 a kilowatt hour, which is 1/5 the cost of the batteries that are there today. So that's what we're shooting for. We're shooting for a battery that can be a big impact in the world where we'll all be driving electric cars that are affordable. A follow-up question was, what are the specific things we'll be doing to get to 5 times the energy density? So it turns out there is no one magic chemistry that can actually get us to those sorts of energy density numbers. So we are focusing on quite a few different things and coming up with some brand new materials that we hope can get us there. An example of that is moving to ions that have higher number of charge compared to lithium. So lithium has a +1 charge. We're hoping to go to ions that have +2 and +3 charge. These sorts of chemistries can ultimately make a big impact. They haven't been studied a whole lot, but we hope to study them in the hub and make a big difference to the energy density of batteries. Alexandra asked, is there a Moore's law for batteries? So Alexandra, the answer is yes and no. It turns out that in batteries, energy densities evolve approximately 5% a year. This is obviously very different from Moore's law in semiconductors, where the energy, or in their case, the performance doubles every 18 months. There are many reasons for that. The first of those, I think, and the most important, in batteries, we're trying to change chemistries and materials each time we want to make a different battery with higher energy density. In semiconductors, one can change feature sizes to make the performance better. It turns out that those sorts of engineering advances have already been done in batteries a long time ago. You can read more about this in my blog, This Week in Batteries, where I kind of expanded on this concept and explained exactly why battery energy densities evolve at 5% and why Moore's law for batteries is so different from what happens in semiconductors. Another YouTube question is, what is the maximum theoretical limit of energy density of a battery? Turns out that's a very difficult question. What we all think is that if you take lithium on one side and fluorine on the other, you can make a battery that has very high energy density. Nobody wants to work with fluorine, so we typically think of using lithium along with oxygen. The energy density of that battery is 10 times the energy density of batteries today. So we have a lot of room left. But this is based on what we know today about batteries. One of the things we want to do in the hub is really understand those limits and really understand how to define them so that we know exactly where we are compared to where we can be. A question from Dan was, how is the hub going to help widespread penetration of renewables on the grid? Well, it turns out that when you have a lot of solar or wind on the grid, one of the problems you face is that these are intermittent sources. What I mean by that is the sun doesn't shine all the time. When the cloud goes over the sun, there is no solar energy that's coming out of the solar panels. So exactly what do you do about that? One way to counter that is to use a battery. But the problem is these batteries can be very expensive, and that increases the cost of electricity. So in the hub, we're going to be looking at trying to find batteries that are incredibly cheap, that can actually compete with gas-fired peaking plants. If we succeed in doing that, we can get a lot of penetration of renewables on the grid without paying a huge cost penalty. Massimo asked, how do I get to be a battery scientist? Well, great question. You can do exactly what I did if you want to become a battery scientist. So I was a chemical engineer, but I got into doing electrochemistry a long time ago. So I described myself as an electrochemical engineer, and so I became a battery scientist by going down that path. But you could also become a battery scientist if you're a mechanical engineer and if you're a material scientist. If you ask me what is the most important thing we need in the next 5 to 10 years, it turns out that we really need to be focusing on new electrolytes that we can use in batteries. What that means for you is that try to become an organic chemist. An organic chemist who understands electrochemistry will be a big need in the future. Thank you so much for all your questions. This has been fantastic, and I had a lot of fun answering them. One thing you guys can do is, if you have more questions, post them below in the comments section, and I'll try to get back in there and answer more of these questions. Thank you again.